what I want to show you is called a waveguide. The purpose of a waveguide is just to guide wave energy. So in the lab, this is useful in any scenario where there's a path between our laser and the sample that we're studying that's not line of sight. So whenever we have to restrict the direction of the transmission of light energy along a certain path, this is a technology that's really useful to us in the lab, but it's also really easy to demonstrate at home. So what I have here is just a jug of water with a hole in the bottom. And if I open the lid so that air can start replacing the water in the jug, I now have this stream of water coming out. And what I want to show you is that we can use this to trap a beam of light from this blue laser. So if I get this at the right angle, then I have light trapped in this water stream. So the way that you can imagine this working is by thinking of light as a ray and picturing a series of reflections inside the water stream. The fundamental principle here is just that we can trap light inside this water stream with a series of reflections, which are light matter interactions. And we're working with visible light in our lab most of the time, so our intuition is really useful, but I just want to formally rule out some other options we have for guiding the transmission of light. So do any of you guys know whether I can use light to change the direction of other light? Okay, well, the answer is no. A quantum of light energy is a photon, and photons don't interact. So these intersecting can't cause the same effect as like the reflection that we see in the waveguide. Light does interact with gravity if you're thinking about something like a black hole, but it would be impossible for us to generate a gravitational field strong enough to be useful on this length scale. So we're stuck with the really intuitive solution, which is to use the interaction between light and matter to change the direction of light. So this waveguide will work with all different, will work with most of the visible spectrum. Do any of you guys know what the wavelength of light is? Visible light, like order of magnitude? So we're working with light that has a wavelength around like hundreds of nanometers. And this water waveguide, the diameter of the water stream is around a centimeter because I just poked a hole. So this is enormous relative to any of the light that we're sending through. And if we wanted to design it so that only one color could be guided, we would have to make this a lot smaller, like on the order of the wavelength of light. But it's possible to design it that way. Now that we're using red, maybe you noticed the effect isn't as convincing here. You can see a lot more with blue. And that's related to a less relevant light matter interaction, which is fluorescence. So something in this water, like in Matthew's video, is interacting with the blue light. So there are molecules of something in the water, and the electrons in those molecular orbitals are being resonantly excited by the blue light and emitting light back at us, so that the water looks like it's glowing. It's water you can buy in the grocery store. This is just tonic water. So it's glowing because it contains quinine molecules. And people drink quinine because it can treat malaria or help prevent malaria. But it's also cool for demonstrations like this because it's fluorescent under blue light. You probably already know this, but there's an order of energies to the visible spectrum, right? You can tell that because this light is red, it's imparting a lower energy, and that's why the quinine's not excited. So if I shine a light beam at this pool of water, then you can see that the reflection is moving when I change the angle of the ingoing beam, right? So we can use that relationship if we know one material property of the materials making up the reflective interface, which is the refractive index. If we know the refractive indices of air and water in this case, then we know how these angles are related, and we can design this waveguide so that light reflects continuously inside the water stream. The goal when you're designing something like this is total internal reflection. If I design this correctly, I could make sure that most of the light is reflected, ideally all of the light. So is that happening in this case? You guys can tell that, like, in this case, some of the light is escaping because we can see it, right? If this were working perfectly, all the light would be going into the bucket. this waveguide, you can recreate it using glass. This is a really flexible fiber of glass that I'm holding. These are installed underground in any cities that have optical fiber internet. I'm gonna try to fire up this optical fiber. Yeah, so here I'm shining light towards the camera, and you can tell the fiber's taking it all the way behind me. And I have to mess around with the angle so the light is guided. That was everything I wanted to show you.